Hi, my name is Adrian, and I did a Hegel practicum on continuous cellular automata. To start off, I want to first tell you a bit about what a cellular automata is. A cellular automata is a system in which we update the state of the system based on a set of rules. For example, in the game of life, we have a grid of cells and we turn each cell on or off based on a very simple rule, and that is that we count the direct neighbors of each cell, and if they are within a certain range, we turn the cell on or off. And using these very simple rules, we can already get quite interesting terms. During the practicum, I implemented Lenia, which you can see running on the screen right now. It's a continuous cellular automata that has been derived from the game of life by introducing very simple new rules, including continuous time steps instead of the discrete ones we had with the game of life, and the introduction of kernels, which allow us to not only evaluate direct neighbors of the cell, but also neighbors that are further away. I implemented all of this on the GPU to get my implementation to be as fast as possible. One consideration I took while implementing this was the comparison between fragment and compute shaders, and as it turns out, fragment shaders are way more performant for this type of task, so I used them moving forward. I also implemented the linear steps using fast Fourier transformation, and as it turns out, fast Fourier transformation can be a lot faster for this when simulating linear steps, depending on our configuration. If we want to evaluate a lot of neighbors, the fast Fourier transformation improves the performance of the linear step quite drastically, and if we only want to evaluate very few neighbors, it has little to no effect or can actually make our performance worse. I spent the second half of my semester looking at particle linear. Why did I look at particle linear after linear? Because linear has one big problem, and that is that we can have patterns that converge towards infinite mass, an example of which you can see right now. How does particle linear alleviate this problem? It does so by introducing particles which we simulate instead of individual cells, thereby ensuring that the mass, which is equal to the number of particles we have, always stays constant. I started off with implementing this again on the GPU, but discovered that we can improve the performance quite a bit by only evaluating particles that are quite close to a current one when performing a step. And by implementing this on the CPU, I was actually able to outperform the GPU implementation by quite a margin. And I achieved near linear runtime, which is quite interesting because the trivial implementation of particle linear is of order n squared. So what am I planning to do now after I've implemented both linear and particle linear? I'm actually planning to use the implementation for particle linear in my bachelor thesis, in which I want to take a closer look on particle linear, especially on pattern discovery in particle linear. Now that's the end of my short presentation. I hope that you enjoyed it and that maybe I was able to light a bit of a fire for continuous cellular automata in you as well.